Hello, Algebra 2 Honors. So in this video, I'm going to be going through some of the basics of our graphing unit. So this mini unit is not in our textbook. It is content that I'm going to give you on handouts and worksheets. I already gave you some of the paper today. That is homework you're going to do over the weekend. And last week I gave you a paper and I asked you to do some things on it. And now I'm going to fill in the blanks of what was missing. And that's what this video is about. So first thing is I mislabeled this. This should have been graph unit number 1, and I should have called this packet number 1. So write packet number 1 at the top of this. And I gave you a physical copy of this document, but it's also attached to the first graphing unit homework assignment in Schoology, so you can find it there. It will also be in the shared drive, as always, because every document I give you is in the shared drive. Okay. And if you ever have trouble finding anything, let me know. Okay, so we're going to be looking at graphs of specific functions, but we need to get some key terminology. So I know you already know domain and range, but I want to just really emphasize domain and range in the context of a graph. So if I have, for example, a parabola, the domain of a parabola, the domain of a quadratic equation is all real numbers, because this graph goes forever to the right. I can plug any x value in I want to a quadratic equation. So the domain is all real numbers. And an interval notation, negative infinity to infinity. I'll usually, for all real numbers, just use the capital R because it's faster to write. Another quick example is, what if I had a function that was in pieces and linear? Something like this. Then the domain would be the furthest left point. Let's say this was -4, and let's say this was, 5. Then the domain is the set of all x values you can plug in. So it's the set of all x coordinates on the graph and the set of all input values to the function. So this domain would be everything from -4 inclusive up to 5. And as I'm doing this video, I want you to have this paper out. I should have said that already. Have this paper out, and I want you taking notes on this. And then I'll show you how to finish the document. Okay, one last example. Sometimes we're going to see in the future, especially in chapter 8, I think, or 9. I forgot the chapter number. We're going to see graphs that have holes in them. And so we're going to have functions that might come over here and then have a hole in the graph and then come over here like this. Let's actually, just for the sake of an example, let's say this comes up and then goes like this forever to the right. So let's say the least x value here is -4. And let's say this hole in the graph is at +4. Well, the domain is the set of all x values you can plug in and get an output. Well, you can plug in anything except, you can plug in anything from -4 to the right, except +4 is not in the domain, because if you drew a vertical line through +4, it doesn't hit any point on the graph. It goes through that hole in the graph. So in this case, the domain is all real numbers from -4 to 4, union all numbers from 4 to infinity. That's my little example there to show you what it might look like if there's a little hole in the graph. Make that a little smaller for the notes. Okay, great. The range, the set of all second coordinates. So the range of a parabola, for example, let's say the vertex of this parabola, that's the point at this minimum, is 2, -3. Well, that means that its lowest point is at -3, and the range is the set of all y values that the function reaches. Well, the minimum y value is 3, and it goes forever up, so it reaches all the y values above it. So the range in this case is -3 to infinity. Let's see. Just that piecewise example, if I have a piecewise linear function, meaning I've got linear pieces that make up 3, in this example it's 3 parts, then if this height is at 5 and this height is at, say -4, then the lowest point is -4, and it reaches every y value somewhere. So at every y value, like this y value, if I draw a horizontal line, it touches the graph somewhere. So that means this y value is in the range. So the range in this case would be -4 to 5. Okay. And then we're going to see examples where we're going to see examples in the future in this course where there's something called a horizontal asymptote. Let me show you an example. Here's a function that comes up and it gets closer and closer and closer to this horizontal line to the right, but it never touches it. And on this side, it gets closer and closer to this horizontal line, and then it goes up. So example of this would be like y equals, this example might be y equals -1 over x plus 3. So this value here would be 3, that height. And if you go to Desmos actually and go try to graph this, y equals -1 over x plus 3, you'll see that the graph roughly looks like what I've drawn. And what's in the range? Well, the graph reaches all heights from -infinity up to 3. But if you were to draw a horizontal line at 3, you'll see that it doesn't touch the graph anywhere. So 3 is not in the range. So the range is everything from -infinity up to 3, but not including it. And when you go past 3, there's graph at a height of 3.01, 3.1, etc., all the way up to infinity, as high as you want to go. Because all these values above, any value I pick here, if I draw a horizontal line through it, it touches the graph somewhere. Y equals 3 is the only horizontal line that doesn't touch the graph. Okay, great. Now, some quicker ones. First off, before I forget, I have a typo here. So do you see where it says y-intercepts? A y-intercept is when x equals 0. So change that y right here. Change that y to an x. That was a typo. Intercepts. An x-intercept of a graph is anywhere the graph touches the x-axis. Like here, oops, here, here, and here. And if I had the function f of x, this is where the function equals 0. In other words, this is where y equals 0. Okay, it's where the graph crosses the x-axis. In the future, next semester, we're going to see graphs like an ellipse. An ellipse example, you don't need to know this for this unit. This is just next semester, we're going to see graphs that look like this. This graph has 2 x-intercepts. And just for fun, the equation of this graph might be something like x squared over 16 plus y squared over 9 equals 1, for example. And you see this, both x and y are squared, so it's not a function. It doesn't pass the vertical line test, but it does have 2 x-intercepts. And if we were to plug in y equals 0 into this equation, this would be gone, and we would get x squared over 16 equals 1, x squared equals 16, x equals plus or minus 4 if you take square roots of both sides. So you would, the coordinate of this point would be 4, 0 and -4, 0. So those are the 2 x-intercepts. So to find an x-intercept, plug in y equals 0. To find a y-intercept, plug in x equals 0. And for functions, it's great. Y-intercepts, there can only be one if it's a function, because the y-axis is a vertical line, and a function passes the vertical line test. And a y-intercept is where a graph crosses the y-axis, like right there. So this is at f of 0 if it's a function. If it's an ellipse, it's not a function, and therefore it could, in certain circumstances, have 2 y-intercepts. And a y-intercept is when x equals 0. All right, extrema, absolute maxima. A function may, at times, have an absolute maximum point. like a parabola that goes like this. Its maximum point is the vertex in this case, and maybe this is 2, 3, for example. A maximum point is the point at its highest value, at its highest point. And in this case, the max value of the function is 3. So when we refer to max value of a function, we're talking about the highest or the greatest y value that the function reaches. When we're talking about a maximum point, it may, in different contexts, refer to the point at that highest point. So then you would write the coordinate. So maximum point, maximum value. Maximum value and minimum value is always a y value. Okay, there are some functions, we'll see this in the spring, there are some functions that reach its maximum value over and over and over again. So this might be, we're going to see this when we study trig. This function reaches the same max value over and over again. So it may reach its absolute max, its maximum point, many times. Minimum is exactly the same idea. One example is absolute value. The absolute value graph has a minimum point at 0, 0, and its min value is y equals 0. And this is y equals absolute value of x. That's the graph there. Okay. Some functions have no max or min at all, like y equals 1 over x, related to that example we saw a little bit ago. That graph has a part of the graph that goes forever up and a part of the graph that goes forever down. So there's no max and no min. No absolute max. And no absolute min. Okay, symmetry. There are 2 types of symmetry for graphs. Graphs with even symmetry are symmetric over the y-axis. For example, y equals x squared. Y equals x squared is a parabola that is symmetric over the y-axis. And if I write it as a function, it'd be f of x equals x squared. Every even function satisfies this condition, and this is our test for a function to be even. And if a function is even, it's reflective, it's symmetrical over the y-axis. Well, if I have f of x equals x squared, what is f of negative x? It's negative x all squared. But if I square a negative, I get the positive. And x squared is the original f of x. So what I have is f of negative x is equal to f of x. So the x squared function is even. Every function where it's x to an even power, like 6, is an even function. That's where it gets its name, actually. And so f of negative x is equal to negative x to the 6, which is equal to x to the 6, because if you raise a negative to the 6th power, it's even, and that's f of x, and that's okay. All right, odd symmetry. A graph that is symmetrical about the origin, symmetric via 180-degree rotation around the origin. Okay, so odd symmetry is a little bit harder to visualize at first, but you might not be surprised that f of x equal to x cubed is an odd function. So f of negative x is equal to negative x cubed. And that is equal to negative x cubed. Because if you cube the negative, it's still negative. If you cube any negative number, it's still negative. So these two are the same. When you raise a negative number to the 3rd power, the negative stays. So notice that this is negative x cubed is negative f of x. So if I plug the negative into an odd function, that negative is preserved, and I can actually pull the negative out to the front. So I have f of negative x equals negative f of x. Now, what does the graph of x cubed look like? It looks like this. And if you were to reflect x cubed over the y-axis and then reflect x cubed over the x-axis, you get the same graph. Because if I reflect it over the y-axis, it looks like this. And then if I reflect it over the x-axis, it would come back to the same graph. So that's one way to think of odd symmetry. Another way is to think about this. A graph is odd if you can rotate it 180 degrees about the origin. Now I know this slid a little bit. If you can rotate it 180 degrees about the origin and the graph is the same graph, then it's odd. So symmetric via 180 degree rotation around the origin. We'll see some other odd graphs later. Horizontal asymptote. A graph with a horizontal asymptote is a graph where the following happens. So here's an example. Suppose a function comes up and gets closer and closer and closer to this horizontal line. Let's say this line is y equals 3. And let's say over here the graph comes down and gets closer and closer to this horizontal line. The graph and the line, the difference between the graph and the line approaches 0. So the gap between the line, the red graph, and the blue horizontal line gets closer and closer and closer to 0. The function, in this case, the function is getting closer and closer and closer to the value 3 because this horizontal line is at 3. An example would be 1 over x plus 3. As I plug in bigger and bigger x, like f of 1 million, I don't know, f of 1,000, I don't want to write a million. F of 1,000 would be 1,000th plus 3. Can you see that as x gets big, this number is going to get smaller and smaller and smaller. So the result of the function will get closer and closer to 3. And in this example, the same thing is true if I were to plug in negative numbers. So if I plug in f of negative 10,000, I'd get negative 1/10,000th plus 3. Now, this is a little less than 3 because I'm subtracting a small fraction, or I'm adding a small negative fraction. So this is a little less than 3. But as this gets more negative, as the thing I plug in the bottom gets more negative, 1 over x goes to 0. And so this whole function gets closer and closer to 3. So that's an idea of a horizontal asymptote. A vertical asymptote is a graph that has a vertical line, and the graph gets closer and closer to that vertical line as you get close to that line. Like this. So the graph never touches the vertical line, but it gets closer and closer and closer to it. It could both go up on both sides or down on both sides or up on one side and down on the other. There's lots of possibilities. Okay, we'll come back to those. We'll say a lot more about vertical asymptotes in like January in a later unit. Okay, so end behavior. This describes the tendency of the graph, or what the graph looks like as x approaches positive or negative infinity. So let's look at an example. What about x cubed? The graph of x cubed is this, and f of x are y values, and at the graph of x cubed goes up like this, and on the left side it goes down. And the way we write this is, as x goes to infinity, we want to describe what happens to y. So let's think about that. As we plug in bigger and bigger x values to the right, what's happening to the output? The output is getting bigger and bigger and bigger. It's going up. So for this function f of x, as y goes to infinity, as x goes to infinity, because that's what we're plugging in, y also goes to infinity because it goes up. What if we plug in x going to negative infinity? So we're plugging in numbers that are bigger negative, larger negative numbers, larger in size, where it's getting more negative. And what's happening to the output? It's going closer to negative infinity because the graph is going down. So now as x goes to negative infinity, y goes to negative infinity. As x goes to negative infinity, y goes to negative infinity because the graph goes down on the left. Some graphs, like x squared, go up on both sides. For example, in this case, as x goes to infinity, the y values go up. So this, because the graph goes up. So as x goes to infinity, y goes to infinity. But it's also true that as x goes to negative infinity, the graph also goes up on the left-hand side. So as x goes to negative infinity, y also goes to positive infinity, because the graph goes up on both sides. Remember the horizontal asymptotes we saw earlier? Remember if this was y equals 3? You may have a function that comes up and gets closer and closer to the value 3. So as we plug in x is getting bigger, the graph is getting closer and closer to 3. Okay, so in this case, as x goes to infinity, what's happening on the right-hand side? The graph is getting closer to 3. It's not going forever up or forever down. It's actually leveling out at a horizontal line. And as x goes to negative infinity, y goes to 3 as well. Because over on this side, as x goes this direction, our outputs are getting closer and closer to 3. Oops. Okay. All right. And that's it. Now, what I want you to do, here's your task. You are going to go through every one of the graphs in here, and you should have the table done already. And you should be able to figure out domain, range, and intercepts. And now I've given you a way to figure out symmetry and behavior and extrema. Let me help you do one. Let's do absolute value of x. Well, absolute value of x, absolute value of 3 is negative 3 is 3, 2, 1, 0, 1, 2, 3. If you graph absolute value, looks like this. That wasn't great. Let me do that a little bit better. There we go. This one goes this way. Okay. And what's the domain? All real numbers. I can plug anything into absolute value. What's the range? The lowest it goes is 0, and it does reach that, and it goes forever up. What are the intercepts? Well, y equals 0, because 0, 0 is the intercept for both y and x-axis. So x equals 0 and y equals 0 are the x and y intercepts. This is an even function. I can tell because the graph is symmetric over the y-axis. Let's show it. F of negative x. Remember, by the way, remember the definition for even. It's good. You have to memorize it. The definition for even, the test for it, is that you need to check that f of negative x is equal to positive f of x. Well, let's check. What is f of negative x? Well, it's the absolute value of negative x. But what's that? The absolute value makes this x. And that is the original function, f of x. So we have just shown that f of negative x is equal to f of x. So it's even. What's the extrema? That's the max min, extreme values. What's the lowest this goes? Well, the min point is 0, 0. That's the point where it reaches its absolute minimum. And the min value is y equals 0, because that's the lowest y value. What's the end behavior? Well, as x goes to infinity, the graph goes up, up, up forever. So that means as x goes to infinity, y also goes to infinity. On the left-hand side, as x goes to negative infinity, y goes to positive infinity because it goes forever up. So it goes up on the left and up on the right. Let me erase that. So as x goes to infinity, y goes to, we're doing the left-hand side. So as x goes to negative infinity, y goes to positive infinity. As x goes to negative infinity, y goes to positive infinity. Okay, all of the graphs here are basic functions like x squared, x cubed, 1 over x. We actually already looked at that a little bit. You're going to fill in all the information based on what we just learned. And I will tell you that I'm about to upload notes for all this, and it has all these completely done, and I'm about to upload that right now into our shared drive. So the answers to this will be in the shared drive. Okay, I want you to try to get all this done by next class if possible. If that's a little short notice, so if you try, and if you don't have the time and can't, it's okay. You can finish it after next class when you have time. But next class will be easier if you can just have this all done and practice it. All right, I'll see you next time. Bye.